Hi everyone, my name is Jake Moore, and for my final project, I analyzed over 1 million flight records from early 2024 to answer a critical question for travelers and airlines. Can we predict flight delays using logistic regression? Specifically, I wanted to know if we could predict the likelihood of a delay based on only operational factors, so using things like origin airport, scheduled time, flight distance, and day of the week. So starting off, you might ask, why flight delays? I was curious about applying logistic regression into a real-world context and understanding different patterns and predictors, and kind of exploring how data-driven models can improve efficiency in scheduling at an airport level. My initial motivation was that if we can identify high-risk flights in advance, it would allow airports and passengers to plan more efficiently. I sourced my data from Kaggle, covering over 1 million US domestic flights from January and February 2024. And to be clear, each row in this dataset represents a single scheduled flight leg. Moving into my methods, I started by cleaning the data. I removed canceled flights and also filtered out delays, which was caused specifically by weather or late arriving aircrafts. I did this because I wanted to isolate the variables an airline can control, like scheduling and airport logistics, and exclude random weather events. This reduced my dataset by about 132,000 rows. After cleaning the dataset, I engineered several features to make the model more usable and accurate. For the time fields, I standardized 24-hour values. Any 2400 entries were replaced with 0, and all times were broken into hour and minute components before eventually converting them to total minutes. This gave me consistent numeric time variables and made it a lot easier to calculate delay time. I also credited the target variable, delayed equals 1, for flights 15 minutes or more delayed, which is the FAA standard. Finally, I kept the top 50 busiest origin airports as individual categories and grouped the rest as other. I did this to keep the model more stable as there was over 300 categories for airports. This preserved all the major hubs without overwhelming the logistic regression model with hundreds of dummy variables. Looking at the results of my clean data, this pie chart was my first major finding. In the specific filtered dataset, nearly 56% of flights were delayed. This is surprisingly high and highlights just how widespread operational delays were in early 2024. I also found that origin airport is a massive driver of delays. The bar chart below visualizes the top and bottom airports by delay percentage, and you can see that major hubs like JFK and Newark had delay rates of over 80% in the sample, but Hawaiian airports like ITO had delay rates as low as 5%. This suggests that where you fly from is the strongest predictor of your actual schedule. Going into more visualizations, day of the week also played a role. This plot shows the delay rates by day of week. Friday, which is in red, consistently showed the highest delay rates. This could be due to volume or other variables not accounted for, while midweek days like Tuesday were significantly more reliable. Alright, so going into our logistic regression model, looking over our confusion matrix, we can see how the model performed. We found the model is correct 64.5% of the time. Our model catches 58.5% of actual on-time flights and catches 70.5% of actual delayed flights. And we found our model has a 70% overall ability to predict. It is important to note that it looks like our model is better at predicting actual delayed flights versus on-time flights by quite a bit. The ROC curve shows how the model performs across every probability cutoff, not just the default 0.5. Instead of giving us a single accuracy number, it shows the full range of trade-offs that the model can actually make. On the y-axis, we have the true positive rate, and it visualizes how well our model identifies on-time flights. While on the x-axis, we have the false positive rate. And this shows how often the model accidentally marks a delayed flight as on time. The diagonal line in red shows what a random guessing model would be, or a 0.5. And our curve gives us an AUC of 0.7. And this generally means that our model performs better than a random guess model, although a perfect prediction would be an AUC of 1. So still a little bit of work to go. These charts below shows which factors most strongly push delay odds up or down. Starting with the green bars on top, this visualizes our most negative coefficients, meaning they're less likely to be delayed in comparison to our reference airport. It is mostly smaller regional airports located in the southern part of the United States that experience these lower delay odds. In contrast, the red bars show the top factors that increase delay odds. This visualizes our highest positive coefficients, meaning they drive delay odds up. It is mostly larger airport hubs located in the northern part of the United States that experience this higher delay risk. Alright, now going into some of our limitations. Time scope was a big limitation as our dataset was only 2 months long, which is a relatively short time frame. This means that our model might not generalize to other times of the year. For example, I found that generally northern airports, regardless of size, tend to be more delayed in our dataset. This could be due to snow or seasonal patterns. Also, our delay threshold, we treated delay as a binary 0-1 problem at 15 minutes or more. This simplifies the problem but also loses a lot of detail. For example, a flight that's 14 minutes late is considered on time by our definition, and a flight that's 5 hours late is just delayed. We don't differentiate based on severity of delay. And generally, our model doesn't account for that difference. A potential extension could be modeling the actual delay duration, though that can be a lot more challenging. And finally, model bias in the chaos. The logistic model showed bias in predicting more delays or false positives. This could be due to the class distribution or the fact that we also used a 0.5 probability cutoff. This could be adjusted if we wanted to. So to wrap up, let's look where this project could go next and how these insights could be actually used in practice. We could incorporate more features. One of the biggest improvements would be adding weather data and airline information to the model. Possibly including destination airport could capture route-specific delays. For operational use, our model could still be useful and it could be used to focus mitigation efforts on Fridays and at congested hubs, since those are clearly the riskiest conditions for delay. Our model can give simple operational tweaks, like giving planes more turnaround time on Fridays at large airports to make a bigger impact. And the next step for a deeper analysis would be to analyze a full year of data to capture seasonal trends in specific airlines. We could extend our model to predict how long delays will last, not just whether they will happen or not. But that is a lot more complex regression problem, but even being able to recognize delays into categories like short versus long could be useful for planning in the future. To wrap up, we were able to build a predictive model that performs moderately well in distinguishing delayed flights and on-time flights. Our accuracy of 65% is a big step up from our initial baseline of 56% we saw in the pie chart at the beginning of the presentation. So there is some predictive value in the features that we implemented. Some of our key findings include that the most impactful predictors turn out to be actually when and where the flight departs. We found that Friday is the worst day for delays, and large hub airports massively increase delay chances. So to answer our question, can we predict flight delays? To a degree, yes, we can, especially if we know the airport and the timing. We can flag higher risk flights, but there's still a lot of unpredictability remaining. In conclusion, this project was a great introduction to logistic regression and provided a valuable look into delay patterns. It provided me with the foundation for predictive modeling in the future, and with future enhancements, we can ultimately get closer to answering our question with greater confidence. Thank you for listening to my project.